So let me start this week's lectures. So I just want to spend some time reviewing what we've been doing so far and sort of explain its sort of significance in some way. So let me just read. So in the last class, if you recall, we did this Gauss Markov theorem, and the basic idea was the following: that we took a concept called best linear unbiased estimators. Let me copy this. So in this, the idea is that you're trying to estimate an estimable linear parametric function. So P transpose beta already assumed to be estimable. And we already have many conditions on when a linear combination is estimable or not. That's we've done before, but let's say assume that. Then it says we define what's called the best linear unbiased estimator, called blue. That means it has to be unbiased. So this E of A transpose Y is equal to P transpose beta. That is, the estimator has to be unbiased. Then its variance has to be less than any other linear estimate. So who also is unbiased? So you take a linear estimate unbiased, its variance will have to be larger than the given variance you have. Then that's when you call your estimator as blue, as the best linear unbiased estimator. And the Gauss Markov theorem told us that, well, it gave us a nice way of finding the best linear unbiased estimator. So it told us that, so I'll bring it down here. It told us that if you have a linear model, if you have an estimable linear parametric function, then the least square estimate is the best linear unbiased estimator. Okay, that's what the Gauss Markov theorem told you that. And just a couple of remarks for this, and then we can sort of move on in some sense. Let me just go back here and make it a little bit smaller so I can write a little bit longer. Make it a little smaller. So I can write a little bit more on this page. So these are things we did last time. Last class. So this, I want to make a couple of comments before I sort of move on. So a couple of comments. Or just remarks more than comments. Like discussion on the Gauss theorem before I move on. So first thing is that you remember we've done this following. We already said P transpose beta, the linear function, is estimable if and only if the least square estimator was unique, right? Estimator unique. This we had sort of done in the theorem long time back, right? And then we also did this other idea that when can you understand unique? So for example, let's say in the simplest case, we also did this other idea that you take beta, let's say P transpose is just a identity map, let's say beta, that is all components, again, it's all vectors, you put a thing here, all components are estimable if only if we have shown that if X transpose X is non-singular, right? If X transpose X is non-singular. And this anyway gave you a unique a least squared estimate is beta hat would be equal to X transpose X inverse X transpose Y. That's what we had done in this setting before. There's going to be some sort of based on this. There is some understanding. Some we sort of spent a couple of minutes today just understand the significance of the Gauss Markov theorem. So it does say that the least squared estimate is blue, but by blue means it's the best linear unbiased estimator. So the least squared estimate is not the best estimator. It's the best among those that are unbiased and linear. So one should leave open the fact that the Gauss Markov doesn't tell you that this is not the best estimator. It's the best among the linear unbiased ones. That's one thing you must keep in mind. And the other thing you should keep in mind is that this model is very, very general, right? For example, it only assumes that the variances are sigma squared, covariances are zero, that's uncorrelated. And it only assumes the mean is X beta, right? And it doesn't assume anything about the distribution of the model. So the errors could be distributed any way it wants, right? So in many ways, that these are two assumptions that make this the LSE as unbiased as well. Otherwise, it's not true. And not specifying a model will imply that you can't get confidence intervals for that. Okay. Let's write these comments down. So let's call this as let me call this remarks now. First remark is the following. I should add white here. First remark is the following: that the Gauss Markov theorem only says that the LSEs are best among all linear unbiased estimators. So it's the LSE, that's the LSE, the per estimate is best among all linear unbiased estimators. And that's what it says, right? That's one thing. So one word of caution, it does not say, so this is one thing it says, right? Let me bring this down. Best unbiased estimators. It does not say LSE is, it does not say, I'll put a cross here, it does not say this particular, it does not say LSE is the best estimator. So one should keep it, does not say that, right? It does not say, so let me make it, since notes will be read later on, let me write it down. It does not say so potentially there could be other estimators that are non-linear and better. Okay. So there could be other estimators that are biased, perhaps, or non-linear that are better. One thing you should keep that in mind. The other positive thing going for Gauss Markov is that it doesn't assume any other than specifying the mean and the variance. It doesn't assume normality, so there's no assumption of on the distribution. of the model. So only mean is specified and uncorrelatedness, right? So it's important, right? So that's something you must keep in mind. That is, it doesn't add any assumption. So in that sense, it's sort of a very general theorem that's available to you. But at the same time, so one drawback is, okay, it can be generally applied. The other drawback is that there's no or beta hat. Right? You can't give any error estimates because there's no more. Right? Or they can't be this, or they can't be no hypothesis testing as well. There's no hypothesis testing. You can't test. Something you must understand. There's no. So just keep this in mind while doing Gauss Markov. And last time we saw also that if you remember, under normality, so if you assume the errors are distributed as normality weighted normal with mean 0 and variance sigma squared by n, using this, we saw last time, the relationship between the maximum likelihood estimator and the least squared estimator. For that. This also we saw last time, right? So let's just that's something to keep in mind. Now, under normality, there's some sort of a nice assumption as well. Understand? Let's go back to the last class on last week's class. So if you remember, if you look at the last set of notes, of course we did this thing. We had this thing. I showed you that so let me copy this down. The likelihood function, if I copy it, the maximum likelihood function is given by is the same as the minimizing of the least square. Put it back here. That is so take likelihood of beta sigma squared given the data set y bar, that's given on the right hand side. If sigma squared is positive, then it's easy to see that the maximum of this guy is same as the minimum of this person, and that's the other sequence. Very nice. Now I want to just go and address this comment about if no assumption is specified, only mean and uncorrelatedness, we can't do any interval estimates. So towards that, I want to address that. Suppose I assume normality. What can I say about the distribution of anything? Can I say something more? Can I produce confidence intervals for the data? Okay. So that leads to the topic of this week. Of course, I'll just mention the topic and I'll come back and again do examples. And then, but today I will go and do other things in the class. Do our examples after this first set of lectures. Very good. Let me state the theorem. This is called the theorem of fundamental of least squares. Fundamental theorem of least squares. So the theorem is, this is a theorem for today that I'll prove. This is called the first fundamental theorem of least squares. So what does it say? So again, you start with the linear model, but you make a normality assumption. Okay. Start with the linear model. So let's say suppose you have a linear model, let's say y, x beta, and sigma squared, let's say I n cross n. That's the linear model. And you assume that the assumption of mean, you specify the mean, where the error is distributed as is y minus x beta, right? Follows normal with mean 0, multi with normal n, mean 0, and variant sigma squared I n cross n distribution. So then I want to understand, how does R naught squared behave? So let's just recall what R naught squared in a second. So let me just do R squared. Let's say beta hat is the least squared estimator. And let's say R naught squared was the residual sum of squares, right? That is, you let the value y minus x beta hat. You take the L2 norm squared. That's what you do, right? This is what R naught squared was. This is the point at which the deviation from the two data set at the minimum least form. R naught squared was. And then under normality assumption of the errors, what one can say is that the distribution of R naught squared is like a chi-square. So let's just write that down. So very good. So I have sigma squared. I'll assume sigma squared is known. Well, the R naught squared. Then R naught squared divided by sigma squared is distributed as chi squared with n minus r degrees of freedom, where r is the rank of x. That's what we should show. So maybe I should not. Maybe let's not write R naught squared as LSE. LSE may not exist in mission. Sorry about that. Let me write this down this way. I'm sorry about that. Let's say R naught squared is the smallest one, is the minimum for all beta in Rn, Rm, I guess Rn, such that Rm, because x can be x cross n, n cross n is Rm. The x is, let me write this down, remove the problem a little bit. So x is n cross m. Gymnastics break polar, so good. R is rank of x. And y are not just the minimum of everybody. I don't want these going to Great. So that's the theorem. So you can actually compute the distribution at the minimum. So let's try and see how to prove this theorem, and then we'll come back and so the residual sum of squares at the minimum is always distributed as chi-squared. So you can use this now. You can use this to compute various things or even test if the errors are normal and so on. So the proof will go by what's called the SVD. So let me state that, and then I'll just state the theorem, and I will not prove it. I'll come back and prove it maybe at the end of today's class if I have time. And this week I have time, I'll try and do this. Right? So I'll use SVD in a sort of a very specific way. So you take x. So let the singular decomposition, let the singular value decomposition of X n cross M, let's say, be given by rank of X is R. So you'll have a matrix P, right, which is an orthogonal matrix times the diagonal one. The diagonal one, the top will be a D R cross R matrix, a bunch of zeros here. And another orthogonal matrix Q, you put a Q transpose, right? Given by X is equal to this, right? And what are the properties we have of all these things? We have P is orthogonal, so P transpose is same as P transpose P is on this side, so it's IN. So Q is on this side, so Q transpose is equal to Q transpose Q is equal to IM, which is an M cross N matrix, entity matrix, right? And D is a diagonal matrix with so D is a diagonal matrix with non-negative entries, sigma 1 to sigma R and 0. We'll make this a bit pink. It's clear. Make it orange. So that's a singularity. So now what I will do is I just do a simple idea. Let's look at, so this is first thing. This is X. This is something we have to understand, that SVD exists. The second thing I'll do is I'll just compute P transpose X. So what is P transpose X? So if I hit P transpose X, you just think a little bit, right? So P transpose will hit this side first. So this is orthogonal, it'll give an I matrix, right? And that means P transpose on this side is this identity. Then you're left with only this and this. So this, everybody else is going to give you 0 except this part at the top, right? So then, so let's write this down. This is going to be equal to, so we'll have a D R cross R matrix. And this one, I'll call it as only the top part of Q will be there, Q1 transpose. And the bottom part will be just 0. So what is Q1 transpose? Where you think of Q, you split it up into the first R columns and the rest N minus R columns, right? So that's, you split up Q. So Q1 is an M cross R matrix. So maybe you should call it Q1 transpose. Maybe you could Q1 at the top. Q1 transpose. So Q1 at the top, and then you have an M cross R matrix. And I'll just call it as Q2. That's what I'll split the Q up into 2 parts, and that's what's going to survive hitting with the matrix. If I hit this matrix with Q, only the first part of Q will survive. That's what I have. So, right? That's what I get. That's easy to see. So therefore, now let's look at this. Let's look at R naught squared. So R naught squared. Sorry, let's go white again. R naught squared. Well, R naught squared is equal to the minimum of beta in Rm of y minus x beta squared. Norm squared. This is what I have, right? This is what I have. So what is that going to be now? So now, so if you just think a little bit, this is because P transpose X looks like this, like the top diagonal minus this one. We just think a little bit. This is the same as let's put a simple exercise. It's the same as the minimum beta in R. I want to exploit this calculation at the top. So I'll get the same as transpose Y minus P transpose X beta. So it's just that I'm just putting a new value of Z as P transpose Y and a new value of V as. So now let's say I take Z to be equal to P transpose Y, like I said, and let V to be equal to, let's say, the other guy, that's P transpose X beta, which we know looks like this person right here, right? Looks like this guy. Let me copy this down, paste it, make it smaller, not too small. But this guy, I'll lay this person here, I'll move across, and I'll just add a beta. That's what it will look like. That's what B will look like. Right, that's good. So now that means this guy is going to be the same as minimizing R naught squared. Therefore, R naught squared same as minimizing beta in Rm of Z minus this guy. This is the same thing, right? This minus V, the whole square. Okay. Now, so V, let me just put, I'll put the other one first and then come back to it because I put beta here. So I'll copy this guy. And this person, right? Now, if I want to just replace everything by V, that's the same as saying the minimizing over all V in Rn are these P transform like beta, so it's RR, right? It's RR. So R Z minus V norm L2 whole square. But I'll just call it tilde, where V tilde is going to be equal to RV at the top and V0. It looks like. Let me just call this we can call it V tilde. So V is just the non-trivial part of 0. But now you just notice the following. Now this is just if I look at norm of Z minus V bar whole squared, if you just think a little bit, so what is D? D is a diagonal matrix, right? And I'm minimizing over all possible V's, right? So this is just going to be equal to, right? This is going to be equal to the sum. So when does it minimize? When V is 0, otherwise not minimize, right? The V is the same as this top part is 0, right? This is V bar. Let me call this as yeah. When V is 0. So the same as this is going to be same as J equal to all that's going to remain is the last part, that is R plus 1 to N of ZJ squared. Because everybody else is going to be you can just match it to Z. That's when you just make the top part match to Z, and that will all vanish off, and everybody else will go away because this part is supposed to be 0, and you'll only get this. So let me call V tilde awareness. So we'll take V to be like Z's, the first parts of Z, and then the bottom parts are all remain this one. Right. So it means, but what is Z now? Z is transpose Y, right? Z is P transpose Y. Z is P transpose Y. Then we know that Y is normal. So Z is going to be distributed as, this is a simple exercise. Z is going to distribute as normal with mean P transpose X beta and variance sigma squared. That's what Z is. R naught is what? So it's all independent normals with appropriate variances, right? So that means we know immediately that ZJ, ZR plus 1 all the way till Zn is just as normal with mean 0, because that's how P transpose F beta looks like. So the bottom part looks like as zeros, right? Mean zeros. And the variance is just sigma squared IR. Sigma squared times I suitably N minus R. Right? So we'll remove this multivariate normal odds, N minus R. The vectors. But this will imply what? It means that all the Z's are independent normals, upward variances, which will imply that each Zj squared is distributed as EJ squared divided by sigma squared is distributed as normal sigma squared. So by sigma is distributed as normal 0, 1 and independent. This is for J between R plus 1 and N. And this will imply that R naught squared by sigma squared, which is just the sum of j r plus 1 to n of z j squared is like chi squared with n minus 1. So simple proof. The key was that I had to use SVD. And once you use SVD, I have decomposition. I know that if I want to minimize y minus x beta, same as minimizing p transpose y minus p transpose beta. And that's exactly what I get. Very cool. So simple proof. Let's recapture it again and then take a little break. This here. So this is a theorem I've shown, right? So I start off with saying that if you assume the errors are normal, then you know that the residual sum of squares at the minimum is going to be chi squared if you suitably normalize it. The way the proof worked is that you take SVD first. So X looks like PQ transpose. Then you observe that P transpose X looks like this. It's just the top part remains, the bottom part is 0. And so you just observe the following fact that R naught squared is minimum is same as the minimum. If you multiply both the P transpose, the same beta will minimize them, because the one that minimizes this will minimize the same thing as this. Nothing will change because linear functions. Then you know Z is P transpose Y, and you take the vector V tilde as P transpose beta, X beta. This V tilde look like this, the top non-zero part and bottom 0. And Z is like P transpose Y, some vector you have. So this will get minimized over all possible vectors V tilde, where V tilde looks like V and 0. Right? So how do you find those vectors V? You just make them first part as Z and the bottom part as 0 already given to you. So this will always be at least this and is equal to this for the vector V tilde. But then if you look at Z linear to the Y, this is normal. Right? Now that means that these guys are going to be multivated normal with sigma squared R. And that implies that this R naught squared sigma squared is going to be a chi squared n minus 1. So P transpose Y is a linear combination of normals. So I should just leave this as sigma squared. Just sigma squared. There's no. Oh yeah, I believe it was. This is IR. So leave I as. I'll just come back to what I is. Very good. Very nice.